Well, I figured because I'm giving a talk on wireless, that's why they unplugged the PC, and it doesn't work. So I'm going to talk about OSPF, or Broadband Wireless Campus Network. I'm from ASU. If you go down Scottsdale Road, past Old Town, cross the river, and then you come to ASU. It's a fairly big campus in terms of number of students, about 40,000 students just on campus. So I'm going to talk about a wireless backbone campus network that about 2 months ago, the Vice President for Computing on campus called me to see if I'd be interested to give a talk here. So I figured we'll talk about this wireless campus backbone at ASU. What I'm going to talk about is applications for wireless broadband campus networks, why we need the wireless campus backbone. And then in order to go wireless, we need to figure out whether we use optical free space technology or radio frequency technology. And I'll talk about OSPF and how we're modifying OSPF for broadband wireless network. And I'll talk a little bit about ongoing embedded system prototype. Now, application of the broadband wireless backbone, ASU has quite a few large data center storage facility all over the campus. It's an urban campus, very compact, but yet the data centers are distributed in many different buildings. So there's a growing need for multimedia educational material storage and retrieval, education online. So there's a large digital video libraries, and I suppose a lot of the educational material need to be distributed to different buildings as well as to different companies around the valley, such as Intel, Motorola. And so we have also massive data stores. There's a Mars probe that project with NASA in the future that may be piping terabytes of data on campus. There's also research effort on 3D modeling, that sort of stuff. There could be a wireless local area network hotspot. I guess here is a hotspot by itself. So also there's a need for portable wireless multimedia booths. For example, when we run student elections and things of that sort, then the students are out in the public. We need to pull the wire literally over the field in order to have the students vote for each other. So these are some of the applications. I would see basically it's not just a need to access the internet, but for educational purposes, streaming video from one building to another building. So there's a lot of storage area network applications going on in campus. Now, so I went down, went to another building to talk to the Vice Provost for Computing, and he showed me the network diagram that I'm going to show you. Effectively, it's a multiple layer of hub and spoke gigabit Ethernet network. I used to work for the Bell system. I thought in the 70s or the early 80s, we got rid of this hierarchical network, the telephone network basically. And then I found out in the 2000, the IP network is effectively a hub and spoke network on campus. It's a 3-level hierarchical network I'm going to show you later. Now, ASU has 3 major campuses. One, the East Campus. The Central Campus is where most of the students, 40,000 students are. And the East and West campuses have about 10,000 students each. We have a few isolated off-campus buildings. And so what we want is really a scalable and reconfigurable networks, hopefully also a portable network. The solution would be to have wireless broadband. We have to do also distributed storage area network. And what I'm going to talk about is basically making a reliable OSPF protocol for wireless links. All right. So now let's look at the ASU campus backbone, and you'll see why it's a highly hierarchical network. Effectively, it's at least 3 levels of hierarchy, maybe 4. At the very low layer, you have all these switches, layer 2 switches on each of the floor of the building, and each floor would have effectively a building network, which you see on your left-hand side the building 1, building 2, building N. Each would have its own router that connects to one of the 6 major hubs on campus, such as the Computing Commons, the Goldwater building, that's where I am at, and also the BAC at ECA. And at the very top level of the hierarchy, you have effectively the old main building. That's the top box in green there, where you have 2 layer 2 Ether switch they are not connected to each other. And then you have a layer 3 Ethernet switch, which is connecting the 2 layer 2 Ether switch by a 1 gigabits per second Ethernet link. And then there are links going out to the ASU East and the ASU West campus on the top there. And then there's also, some links going out to ISPs and also the U of A down south and the North Arizona State University in the north. So you think about it, effectively, you have 3 levels of hierarchy. There's, you have 5 major hubs there, and the hubs are connected to the main hub at the old main building. Now, the old main building is a historically protected building. It's so old that they lost the floor plan for the building. So they are, I guess the computing center started there, so, that's why they're still housed there, even though it's a very, very old building. So if you look at a typical campus building, what we have is a number of users, each connected to one of these layer 2 Ether switch, which in turn go into perhaps the building MPF, the layer 2 Ether switch that connects to the hub, and then go one level up to the main hub. All right, so now let's look at this whole architecture here. It's strictly hierarchical. All traffic go to old main, got redistributed down. So what we are talking about here is basically we would form an adjunct broadband wireless network, at least connecting the 5 hubs at the top. That is a partially meshed network. We will start with basically a mesh ring network for the 2nd-tier hubs. And then at the very bottom where you have the buildings, I think it would be good to use a mesh network for the 3rd-tier nodes, which are essentially the buildings on campus. It could be a relay network for these buildings so that one building would serve as a wireless relay for another building. So that's the kind of topology we're talking about. It's an adjunct network. The university allows us to plug these wireless cards into the gigabit Ethernet switch, and hopefully, if they trust us later on, we'll we'll merge the 2 networks. Now, we're talking about mesh network here, and even though ASU is not a very big campus, I mean, each side is about a mile across, but yet you have such a hierarchical network. The reason for that, I think, is largely prompted by the fact that, with all these gigabit Ethernet, everybody taking the gigabit Ethernet as a hub and connecting all the other buildings to it. Communication is expensive in the sense that it's in terms of management, it's very hard to form a mesh network. But once you put in wireless links in there, it's fairly easy to form a mesh. So we're talking about partially mesh network. On the top there, we could have the 5 major hubs there being connected, each by at least 2 wireless links. These are point-to-point links going out to the different buildings. Some may have 3 or 4 links going out, and they are operating at 1 gigabits per second. Now, just getting a little bit into the technology side, we look at whether we should be using optical technology or we should use radio technology. And the advantages to optics, there's no spectrum licensing required. There's no multiple path problem. You need point-to-point direct line of sight. The transceivers are cheaper. It's high speed, and you can also use DWDM. You have excellent channel isolation. They don't interfere with each other. There's some security that you can achieve by optics because you have to get into line of sight in order to intercept the signal. Now, the advantages of radio, line of sight sometimes is not mandatory, but for the purpose of this talk, when we talk about radio, it'll be line of sight primarily. It can achieve longer distances. It's more weather resistant. If you have free space optics, effectively the link will be out if there is fog or mist. That's the worst. Rain is still probably okay. But in Arizona, we don't have rain, but still you have a problem, which is atmospheric scintillation because of the hot temperature, and that can take your link out also. If there's less background noise, and radio is easier to point, it's also eye safe. So we actually look at the two technologies, and we're doing both, actually, both the laser links and also the radio link. But when it comes to radio link, you need to worry about the spectrum available. So we look at it, and we've chosen one frequency band that is at the 57 to 64 gigahertz. And that's extremely high frequency. Your 802.11 here is 2.4 gigahertz. So you're talking about 30 times higher in speed. Now, if that frequency band is totally unlicensed, 57 to 64 gigahertz, you get 7 gigahertz of bandwidth. It's totally unlicensed. But the problem with that is that that particular band, you can't go very long distance. You can go about a kilometer, and that's about it. Okay? But for our campus, a kilometer is really almost reaching the north, from the north to the south part of the campus. All right, so we're using that, and that band is so wide that we can use it very inefficiently, both in terms of bandwidth efficiency as well as power efficiency. All right, so we can go optical. We do the experimentation with the wireless laser beam network, collimating it and focusing it, and trying to look at what sort of effect it has on us. All right, so the campus, wireless campus network, there are several approaches to go wireless. One is you can use the LMDS, wireless ADSL technology, basically a wireless local loop technology. It's not a backbone network technology, and it's still a hub architecture. A lot of the wireless solutions these days still employ a hub sort of architecture, like TerraBeam. It's a shared bandwidth, and a lot of people may talk about gigabit wireless network, and they are effectively using wireless gigabit Ethernet. And even though it is advertised as 1 gigabit per second, yet you typically get about 20 megabits per second per link. It's a local exchange carrier model, DSL over ATM. Now, what we are proposing is basically a totally wireless backbone node. We don't look at it as a local loop mesh architecture. Now, what is interesting is that you have multiple parallel pathways, providing a tremendous amount of redundancy. What we try to do is that the 5 hubs, not the top, including the top-level hub, will be connected to each other through a dual ring. So each of the building would have 2 lasers or 2 RF links pointing to other 2 buildings, and it's a bidirectional ring, and so you have 2 pathways at least. It's an internet model, and what we actually are looking at, not just TCP over IP, but we look at one primary application is SCSI. Largely because we talk about video retrieval, that sort of stuff. So also there's a lot of data center applications there. And lately there have been a lot of talk on this iSCSI protocol, which effectively have SCSI running over TCP over IP. There's a lot of debate about whether you should have SCSI over TCP, because TCP reaction time is a lot slower than SCSI itself. So we basically, in our prototype, we have SCSI over IP, which is, we're not taking the approach that SCSI over TCP over IP. We look at fiber channel also, because fiber channel is a very reliable protocol. In a sense, we're looking at fiberless fiber channel. So we have 10-base T, and of course we have TCP also over IP network. Now, the key challenges we have to face is basically the optical link. The propagation is a problem in poor weather. Pointing is also a problem. so you need to spread the beam out a little bit. Power budget, eye safety problem. The data links, we have link failure, node failure, traffic measurements, quality of service control, network routing, ad hoc routing, IP switching, resource discovery, traffic balancing, domain management, and all that stuff. System analysis, how does all these different interfaces like SCSI and Ethernet, how do they work together? Multiple protocol, device mapping, configurations, that sort of stuff. So we're thinking about it from a storage area network point of view. Basically, that is like a storage area network that's distributed over the entire campus. So we talk about mesh network. It's a fragile network. So any link of the network may become inoperative at any time. You know, maybe there's a pigeon flying overhead with droppings, that sort of stuff. So you need to reroute when the link is being blocked. And you're talking about millisecond sort of response time. So you have to reroute within maybe a few milliseconds. It's a very fragile network. The failure of a single link should not prohibit the message delivery. Now, this sort of network is getting close to what is known as the ad hoc network routing protocol. Except these nodes could be portable, but they're not mobile. You could be porting them to an information booth, and you know, but it's not. We're not talking about these things riding around in trucks and things of that sort. So it's a very fragile network. We look at the different protocols. There are a lot of ad hoc network protocol out there proposed, but we chose to use OSPF in the implementation. Now the question then is, how do you make OSPF really operate as if you are in an ad hoc network environment? So you can have different kind of failure, router failure, link failure, and so on. Now, the protocol for wireless optical ad hoc network, we look at link state monitoring, we provision quality of service, we have rapid yet distributed rerouting upon link and node failure, resource discovery and management, and multiple protocol adaptations. Now, let's think about the use of OSPF here. What if the link go up and down very quickly? You're talking about that it go down and you're supposed to detect the link has gone down in about 2 or 3 milliseconds, and you do rerouting right away. And when the link go back up, you need to maybe route back to the original route. So there are several ways to do it. One is you can look at OSPF. If the local link goes down, you can locally trigger a route recomputation. That's pretty fast, but you know, most of the time the delay is caused by the time that it takes to detect the link has gone down. So you have to get all that information from the link layer. It can get all the way up to about 10 milliseconds. Even if you trigger a route recomputation locally, that doesn't take a whole lot of time, but the problem is that if you have the link state information propagated throughout the whole network, that would take quite a while. In between you computing your route tree to everybody have computed the route tree, there's a convergence period when these routes have not converged. So that is a pretty serious problem. What we chose to is that we pre-compute the alternative pathway. Effectively, you know, look at all the scenario where your outgoing link has gone down, and then computed not just the shortest path tree, but also the shortest path tree if this link has gone down, and so on. So we store all that route information in case of link failure. We have the layer 2 telling us very quickly about the link has gone down, and therefore you need to use the pre-computed alternative route. Now, there's still the issue that the links themselves only know about the link has gone down locally. And if you have to react within 2 or 3 milliseconds, you need to worry about the fact that even though you have computed an alternative route to your destination, the other node effectively would create loops for you. One very simple network would be the ring network that we talk about, connecting the 5 hubs. You detect that a local link has gone down, so you send the packet the other way, okay? You got one hop down the other part of the ring, the other guy still thinks that the fastest way is to go counterclockwise, and he send it back to you. In fact, you got basically a loop, and that was the problem pointed out by one of the speakers yesterday. So we think about it, and we thought, if you are dealing with data center sort of application, you really need to make IP a lot more reliable. It's very interesting. The talk yesterday pointed out 3 kinds of bugs you have in the IP routing that cause packet jitter, and all 3 bugs were fixed. And all right. So what we the problem that we're looking at is at the bottom. Is it possible really to retain much of OSPF distributed computation, yet able to route correctly when the link node fails? All right. So how do we do it? We thought about it for a while, and one of the ways we figure out the best to really route correctly during the time of convergence would be to use IP encapsulation. The idea is very simple. I mean, in a lot of ad hoc network routing, what they do typically is that they do source routing. And that's probably the most popular sort of ad hoc network protocol you have nowadays. How do you mix source routing with OSPF? That's the question we ask. We don't want to create really a source routing protocol running parallel to OSPF. So what we do is we try to fool OSPF into thinking it's doing OSPF, but in fact it's a source routing protocol. So the idea is very simple, which is basically IP packet encapsulate multiple times the route is taking. Effectively, you encapsulate the packet pointing to the next hop in your pathway. So by doing multiple encapsulation, effectively you're doing source routing. Okay, so the answer is yes. Multiple path OSPF is IP encapsulation for source routing. The node broadcast link state infrequently. Each node compute multiple path contingent on fault and QoS. Multiple IP for QoS assignments, and use of IP encapsulation to forward packet along pre-computed pathways. So we're doing the prototype over several platforms. We started with the OpNet to test out the concepts. And then we are right now doing a piece of POX sort of router. Effectively, it's an edge router. It's all based on IP. We are doing both the free space laser link at 850 nanometer, running at about 1 gigabits per second. We're testing a link to see how much power is required and so on. We are also looking at millimeter wave radio link frequency at 57 to 64 gigahertz and at 1 gigabits per second. It's applied both indoor and outdoor. So the whole idea is really to break this paradigm or habit of forming hierarchical network. So you're putting all these edge routers. To start with, you put them at the top level hierarchy, the 5 major hubs there, and then eventually you move it down to the buildings themselves so that they themselves can form a mesh network or relay network. And another plan would be to move that even further down within the data center itself. So we're prototyping this. We basically bought a bunch of disks and servers, and we have these cards that we're building, and each of them has 2 laser pointers pointing to the adjacent users. So it's a ring network of sort, and so we're testing out this configuration at this point. So the last one, conclusion. So what we're doing is a distributed router development, modifying the OSPF protocol, and we play with the different sort of transmission technology, and we're currently getting both public and private funding for the prototype of this effort. Yeah.
Thanks, Joseph.